Okay, so that's the algorithm. Let's first see why it is correct. Okay, so just to remind you, so here is the outline of the algorithm. The algorithm basically maintain a set of nodes that you already explored, that you find their shortest path correctly. C, okay, keep growing the set C. Every time I greedily remove a node from outside C with the smallest estimated distance, I choose that to include into C, and I explore that one, see whether I can discover new shortest paths to other nodes. That's it. Okay, so this is exploring. This is first the greedy choose a new node added to C, and then explore this new node, the neighbors of new node. That's it. Okay, so okay, to talk about correctness, I'm going to use a concept just to make it easier to describe. I'm going to use the concept called exit path. Okay, so what is the exit path? An exit path through the current set C is just a path that first this path stay within the set C, and then with one edge to going out, WU. Okay, so this example that I'm drawing here is an exit path. So from S, you first going inside only set C to reach a node. So in this case, W, and then you take one edge to go outside the set C to U. Okay, so it's called the exit, and U is called exit node. So basically, this is a node where you leave the set C. Okay, set C are those root nodes that you already find the correct shortest path. So U is basically the node the first time you leave set C. Okay, and this edge WU is called the exit edge because you are exiting the set C. Okay, that's what it means. Okay, so some more examples. Let's say in this case, the set C has 3 nodes, S, U1, U2. Okay, then S go to U1, and from U1 to U6. This is an exit path because first I stay inside and then I leave this set C through one edge. Okay, so this is the exit path. Okay, or I can go from S to U1, U1 to U2, and U2 to U3. This is also an exit path because I first stay inside C, this S to U1, U1 to U2, and then I leave C through one exit edge, U2, U3 to go outside. Okay, so basically that's the first time you leave set C. You have a path that you need. You have a path that you leave set C. Okay, and so this is also an exit path. If I take, for example, S to U1, and then U1 to U3, and U3 to U5, then this is not an exit path because I mean this is your exit this set C at U3. Okay, so U3 is the exit node going to U5. So if you only take S to U1, U1 to U3, that's the exit path. But if you also go to U5, that's not exit path anymore. Okay, so exit path is only the first time you leave set C. Okay. One last example. Let's say I go. Let me clear what I have here. Let's say that if I now go. I don't have a way to come back. Okay, so in general, if I have a path that I'm stay inside set C, and I first go out and then come back. Oops. If I go out and then come back and then go out again, this is also not an exit path because so the exit path says that you have to first stay in C and then first only leave the set C once. Okay, the first time you leave C. Okay, so this is not exit path either. Okay, so that's just some examples. All right. Now, let's say that suppose in this example, okay, in all the nodes inside set C, we have already computed the correct shortest path distance, okay? And the one outside is those estimates that our algorithm maintains, okay? But if we just look at this picture, okay, say, what is the length of shortest exit path to exit node, say U3, okay? In other words, there are multiple ways, there are multiple exit paths to reach U3 first, as the first node leaving set C, okay? What is the shortest one, okay? So in particular, in this case, I have exit path, for example, I can go S to U1, U1 to U3, that's one exit path, right? I can also go X to U1, U1 to U2, U2 to U3. That's another exit path, okay? A third one is that I could first go S to U2, U2 to U3. These are all exit paths with exit node U3, okay? So what is the shortest one, okay? If you calculate this, the purple path has length 4 plus 6, that's 10. The blue path has length 2 plus 1 plus 6, that's 9. Okay, while the orange exit path has length 2 plus 4. So the shortest exit path to reach the exit node U3 has length 6. In other words, okay, the fastest way to go to U3, okay, through an exit path is 6, has length 6, okay? All right, now I'm going to, let me remove this, but only keep this path here, okay? Now, what is the shortest exit path to reach node U6? Well, in this case, you don't have many choices. It turned out that the best way to reach it is simply S to U1, U1 to U6, okay? You can also ask, what is the shortest exit path to reach node U5? Okay, remember I didn't mark it here, but the U5 right now has an estimate of infinity. Okay, now you note that, okay, U5 is not directly connected to anybody inside C. Okay, so they're not reachable as an exit via an exit path. Okay, so the shortest exit path, there doesn't exist any exit path to reach U5, so the shortest one remains infinity. Okay, so in other words, exit paths can only reach those nodes who kind of have an edge connected from inside set C. Okay, because it has to be able to reach from set C through one edge. Okay, so that's the first thing. Things that I cannot reach yet, I don't have access to them. Number two is that if you look at all this shortest exit paths, what do we find out? What do we notice? Well, we notice that actually the length of the shortest exit path exactly equal to the estimate I have. Okay, so again, think about the just think about the shortest exit path to node U3. Okay, so I want to ask, what is the best way to reach U3 through an exit path? What is the definition of an exit path? The exit path is that I have to first go somewhere inside set C and then going out through one edge. Okay, right? So intuitively, in other words, the last edge has to be one of the edge coming here, connecting to it. Okay, and remember that all the edges inside the set C already have the correct distance estimate. Okay, so if it comes from a node, the shortest exit path is coming from U2, suppose it comes from U2, okay? That means that the distance to this node must be the best way you can reach U2 plus the edge weight of U2, U3, right? So that's if your exit path coming from U2, then the best length, the smallest possible length is that you first take the best distance to U2 plus 6. Okay, in other words, the distance will be 3 plus 6, okay, which is 9, bigger than this case, okay? So remember, during the update, our algorithm, what happened? Our algorithm essentially maintains every node you computed correctly. I check whether I can reach U3. So when I compute it, when I explore U1, I check whether I can reach U3 better, or when I computed when I explore the U2, I check whether I can I perform update operation to U2, U3 to see whether I can reach U3 through a better way. Okay, and the red one, the one we maintains here, is the best that we found so far. Okay, that means that just because of the way the algorithm performs, this estimate we have here intuitively is actually the best, the shortest exit path length to go from S to U3 at this point. Okay, so this is the intuition. Okay, so we're not going to prove this correctness of Dijkstra algorithm formally. I just want to make sure that you understand the intuition. Okay, all right. So okay, some observations of this exit path. Okay, the first one is that any path from S to a node U outside C has to start with an exit path. Okay, so if this is your set C, so if this is your set C and you have S here, okay, and you have some node U outside, okay, so any path between them, okay, any path going from S to U, it has to start, you have to leave the set C sometime, okay, and the first time you leave set C, that's your exit path. So for example, for this path, it leaves set C through this edge. At some point, you have to go from inside C to outside C, right? And let's say this is the edge that's going from inside C to outside C, and then the path going from beginning till this point is basically an exit path. Okay, so any path from S to U has to start with an exit path. Okay, so in other words, this path can be decomposed into first an exit path, which is this purple one, and then let's say this exit path reach W, then plus the path from the exit node W to U. Okay, so any path can be decomposed this way. Okay, it has to always start, beginning has to start with the exit path. Again, the reason is because S is inside C, U is outside. To connect them, at some point, you have to leave set C. And the first time that happens, that's your exit path. Okay, that's how you exit set C first. Okay, all right. So this is just another example. In this case, you have a path S to U, and the exit path is basically from S to Y. That's your exit path. So this path can be decomposed to exit path from S to Y, and then plus the path from Y to U. Okay. So that's a simple observation. The second one is basically what I already said, okay? So if inside our algorithm already compute the correct shortest path distance estimate, and then outside, and we update explore their neighbor as we described in the algorithm, okay? Then turned out what happens is that for any node outside the set C, the shortest exit path with this node as the exit node must have what we computed so far, the estimate computed so far, is exactly the length of the shortest exit path to reach this node. Okay, so, all right. So with this observation, now we're ready to prove the correctness. Again, as I said, you don't have to worry too much about the details. I'm trying to explain the intuition behind it. Hopefully, you see the intuition why this is the case. Okay, so on the high level, we're going to prove that the Dijkstra algorithm, remember the Dijkstra algorithm will have a while loop. Okay, so here actually, this is our algorithm. We'll have a while loop, and every time each iteration of while loop will add one more node, will reach one more node and exploit and add this node to our set C, right? So, okay, so we're going to argue that this while loop satisfies the following loop invariance, which is that at the beginning of each while loop, the distance estimate we compute in set C are already correct. Okay, and also the second one is what I claimed just now, namely for every node outside set C, the estimate stores our current estimate stores the length of the shortest exit path to this node. Okay, so we can at the beginning note that set C is empty, so this loop invariance trivially holds. Okay, and inductively, we want to argue that if this holds so far, then after we process the next node using the while loop iteration, this still holds after this while loop iteration. Okay, and if we can prove this inductively in the end, when there's no node outside, then by the first invariance, that means that we have computed shortest path distance to all nodes correctly. Okay, so this is This is just saying that every time we add a new node to our set C, that node, we found the correct shortest path estimate, okay? The second is just saying that for all the nodes still outside the set C, what we estimate so far is the length of the shortest exit path to it. That's it, okay? All right, so, and this is the algorithm. And how do we prove the loop invariant one? This is the most important one, okay? In other words, remember, what does the algorithm do? The algorithm at each iteration pick the node from outside C with smallest estimated distance, okay? So what I want to argue is that this choice, this greedy choice of the next node that I'm picking, okay? So let's say U is the one that we picked. U is the node outside C with smallest shortest path distance estimate so far, okay? Then I claim that then this estimate right now has to be the length of the shortest path from S to this node, okay? In other words, this node with smallest estimate right now has already found the correct shortest path distance, okay? That's a claim, okay? So how do we prove that's the case? The proof essentially is kind of, it's a little bit like a contradiction. I'm going to use a picture to show the idea in a minute, okay? So basically what we're going to prove is that if we want to show, in fact, let me just, oops. So let's just use this example first, okay? So in this case, U is the node that, so U is the one, the node outside C with smallest estimate. Okay, in other words, node U is the node where what we picked in the current iteration. Okay, so we picked the U. Now, what does this mean? We know that we already have an estimate U, and that means that I have a way to reach this 3's predecessor. Let W be its predecessor, okay? That means that I have a path going from S to W, and then from W to U. This one, the length of this red path S to W plus H UV is, so this is the path that give me this estimate, okay? All right, so we already found a path to reach U with this estimated distance, okay? Let the red path be this one, okay? Note that also this red path has to be an exit path, right? Because the way we found the U is always that we found the, we have its predecessor W plus an edge, and the predecessor W can be reached by a path inside the set C, okay? All right, so we already have this one whose distance is you estimate, okay? To show that this red path, our goal is basically to show, okay, the red path is shortest, okay? So our goal to show that the red path is shortest from S to U. Okay, how do you show that? Well, the natural idea is that, okay, you pick any other path from S to U, and you argue this other path has length longer. That's it. You want to show S, this red one has the shortest length, okay? So let's now pick an arbitrary other path, okay? So this is, let's pick an arbitrary path from S to U, okay? If I can show that the red path is shorter than this new path I'm taking, then the red one must be the shortest because this is any other path, okay? Okay, in fact, let me change it to be any other. Okay, all right, so this is what we want to do. Now, consider this path from S to X to Y and so on. Remember what we said is that any path can always be decomposed to be first an exit path and then together with another path, right? So because you have to leave, this new path has to leave set C somewhere, okay? And then let XY be the first time that it left the set C. So this green one is the exit path, plus this purple one. This is my new pass. Okay, all right. Now, the thing is that this is the exit pass. So what is the length of this? Well, the length of this green pass has to be at most y dot estimate. Why? Because the current estimate at y contains the shortest possible exit path, right? So this path, let me write it here. The length of this path equal to the length of green path plus length of purple path. Okay, so I'm going to erase this. Okay, so we see that this path can be decomposed to be the green one plus the purple one. Okay, and what is the length of the green path? The length of the green path must be smaller, bigger than the shortest exit path to y. Okay, the length of the purple path I don't know, but because this is positive, all the edges has positive weights, I know this must be bigger than 0. Okay, so that's what I know. Okay, that means that the length of this other path has to be bigger than the shortest exit path to y, right? But what is the shortest exit path to y? Remember, we said that by our loop invariant assumption, that is basically the estimate we have so far. Okay, that means that the length of this new path has to be bigger than the estimate to the exit node y. Okay, on the other hand, u is the node with the smallest estimate. In other words, this is bigger than u dot estimate. That means that the length of this new path from s to y, from y to u, is bigger than u dot estimate, which is the length of the red path. Okay, so hence this path, this green plus purple path, is longer than the red path. Okay, and this works for any other path other than the red one. As such, the red one must be the shortest path to reach you. Okay, so that's the idea. Okay, all right. So I put it down more formally here, but the idea behind this really is just what I just said. Okay, again, what this is saying is that if we pick u, who has the smallest estimate right now among all possible nodes outside, okay? And remember that by our assumption, the loop invariant, the u estimate is the length of an exit path to reach u. Okay, so we already found the red path to reach u with the current estimate. Okay, now if this is not that, now to show that this red one has to be the shortest, we consider any other path to going from s to u. Say I pick an arbitrary one, say the one which is the green plus the purple here, okay? And any other path has to leave the set C somewhere. That means that this other path can always be decomposed to be the first time they leave set C, let's say the exit path to y plus this purple one, okay? But then the length of this green plus purple has to be bigger than just the length of the green path, okay? And the length of the green path has to be bigger than the shortest exit path to reach y, which is y dot, it's bigger than, which is the y dot estimate, okay? All right, so in other words, the length of this new other path has to be bigger than the estimate that we have for node y, okay? But we know that has to, U will pick the smallest. This is where the greedy choice make a difference. Okay, why we have to do a greedy choice? We have to pick the one with the smallest estimate. Okay, since we picked the node with the smallest estimate, that means that the green path is longer than the estimate to U, which is the red path. Okay, as such, the red path has to be the fastest way to reach U. You cannot find another path whose length is smaller than this red path. Okay, so that's the argument. Okay. Okay, so this essentially is really the key to prove the correctness of the algorithm. Okay, but I hope you understand the intuition. And of course, there's another invariant. The second invariant says that the outside the nodes, the estimate has to store the shortest exit path length through C. Okay, and in particular, suppose this invariant holds before we a specific iteration of the while loop, okay, where we picked U, okay. Then after that, we only need to update this estimate. So suppose that before we run a certain iteration, we already have set C, okay, and let's say that in this iteration, we then pick the node U and include this U into our set C, okay. Now, we basically, once we pick this one, when we explore U, okay, now the only nodes whose shortest exit path that change, because shortest exit path is for any other node outside U. Let's take a different color. So all of these other nodes outside U, okay, only those who can reach through U will have new exit path to reach them. Okay, so if this node doesn't have anything coming from U, then the exit path reaching this node doesn't change. So the shortest one doesn't change either. Okay, only for nodes that's connected from U, then that gives us new exit path now to reach them. So we have to check whether that gives us a new, better distance estimate. Okay, but this is exactly what our algorithm is doing. Our algorithm is performing update on all of these edges to see whether we can reach this node through a shorter way. Okay, so the algorithm guarantee that as such, guarantee that after we finish the update operation, each node still maintains the shortest exit path to reach them, the estimate. Okay, that's the second invariance. All right, and that is here's just one example of what I just said. Okay, that's this also helps us to again to see what the algorithm does. Okay, let's say this is the one after the current iteration. Okay, all the nodes circled here. Those are in our set U. Okay, what is the algorithm doing in the next iteration? The algorithm will choose the one with the smallest estimate, which is node U6. Okay, because 4 is the smallest. Okay, so then our algorithm will now include U6 also into our set C. Okay, now I need to also maintain the second invariance, namely all the nodes outside, I still remember the best way to reach them through an exit path. Okay, then who can be affected by including U6? Well, this node use only the nodes that can. So if I have another node here, if this node cannot be reached from U6, I'm just doing some. Suppose we also have this here. Then this node, you don't find any new exit path to this node. Okay, only the nodes where there's an outgoing edge from U6 to them will have new exit path to reach them. Okay, so you have to see that does this new path going through U6 give me a better way to reach this node? Okay, in other words, we have to check, we have to perform update to each of the nodes that can be reached through U6. So we have to look at let's say we first look at the U6, U3. Okay, so you say that do I have a new way to reach U3 through U6 now that we include the U6 into the set C? Okay, and well, we see that U6 has distance 4. A new path as such has 4 plus 1, which is 5, which is indeed better than U3's original one. Okay, that means that, okay, I found a new way to reach U3 with distance U5. And now that also means that my new predecessor should change from this one to this edge. Okay, so you do the same for other neighbor of U6. You say that, do I find a new way to reach U4? Well, this new way to reach U4 has length 4 plus 3, because this is best way to reach U6 plus the last edge 3, and that's 7, which is bigger than what I already have. That means that, yes, this you found a new path going to U4. This new exit path is not any better than what I found before, so I do nothing. Okay, then we check the edge U6, U5. Okay, so and so on. I didn't put the distance there. So this is what we do. Okay, and this is essentially the before and after. Okay, all right. So again, because of this two loop invariance, and we just kind of showed you the intuition that this two invariance holds each time after we gradually pick a new node and then update its neighbors that continue to maintain this two invariance. That's why in the end, after we remove all nodes from outside, after there's no more nodes outside, then that means that the loop invariance guarantees that the algorithm is correct. Namely, we compute the distance to all nodes correctly. Okay. All right. So the note that at the beginning we say that this algorithm works when all edge weights are positive. Okay. So I want you to think about, why do I need this condition? Okay. In the argument we just described, I mean, in particular, in fact, in maintaining the first invariance. Okay. Where did I need this condition that all the edge weights has to be positive? Okay, so I want you to think about this yourself and try to come up with an example yourself that you have a way to the graph G with a source node S, and when you run Dijkstra, you fail to compute the correct shortest path. Namely, you must have negative edge weights. Okay, so have an example where you have negative edge weights where this algorithm fails. Okay, and see, and also ask yourself, why does it fail? Okay, I'll probably come back to this later in future lectures to explain this. Okay, but first think about this yourself. Okay.